Hello, sir. We are from Group 30 and our topic is Smart Fire Alarm System. My name is Lee Wan Jing and now I'm going to start with the background of the Smart Fire Alarm System. Fire incidents have always been a critical issue that must be dealt with on time without any delay to save life and reduce property loss. According to the National Fire Protection Association (NFPA), about 2/3 of US household fires happen in places with no working smoke alarm, misplaced alarms, or alarms with no proper maintenance. Therefore, people are getting more and more aware and realize that early fire detection contribute positively to fire control. For example, during ancient time in the Roman Empire, Emperor Nero enforced the regulation to have fireproof material for walls and buildings. While in this modern era, a fast response and reliable fire alerts plays an extremely crucial role in protecting people's lives as well as their properties. The next part will be the history of smart fire alarm system. The first usable fire detection system was developed using the telegraph in the United States by Dr. William Channing and Moses G. Farmer in 1852. While the first temperature sensors started with the introduction of bimetallic sensor in the 19th century. They are used as the first fire alarm sensor in the fire detection system as they are reliable and durable. While in 1930, the first electronic smoke detector was invented accidentally as a result of an error by Walter Jagger. He was attempting to develop a poison gas detector, but the detector didn't work as expected. After failing several times, he lit up a cigarette and suddenly the smoke detector was activated, leading to the successful invention of the first electronic smoke detector. After that, a flame detector was invented along with the optical smoke detector. Flame detectors are solutions that cater for almost all the applications where fire may occur as they are very sensitive to charcoal, ember, and so on. That's all for my part, and now I will pass to the next presenter. Thank you.
One of the future trend of the smart fire alarm systems is the IoT enhanced automated fire alarming system, like using the IoT technology to integrate the other system in the building to automatically perform the life-saving procedures such as stripping the ventilation system to vent the smoke out, shutting down the power supply of the specific area in the building once the fire is detected. Next, the smart fire alarm system can be implemented with a better evacuation system that includes the voice alert, escape route, and strobe lining. So when the fire is triggered, the voice alert can alert the people in the area where the fire has occurred. So in the meanwhile, the guide of the escape route will be automatically sent to all user mobile phones, and the strobe light will automatically light on the escape route to guide the people to a safety place. The last trend is the multi-sensor detector. Okay, it can be implemented to detect a fire. This sensor can detect the multiple aspects of a fire, such as smoke, using the laser technology and the heat from the fires, all from a single device. So with this system, accuracy may be improved and the false alarm can be minimized.
Thank you, Jai. I'm Xiaofu. Now I would like to continue with the problem statement and objective in our project. The first problem will be carried out is many of the existing smart fire alarm systems do not have a function of providing insight into the condition of fire detection devices. Since it is harder for the user to frequently check whether their fire detection device is working properly or not. The second problem is some of the existing smart fire alarm systems do not show a map to trace the location of those active fire detection devices. Since it's harder for the system to trace the location of the fire detection device that has triggered the fire warning. The third problem is some of the existing smart fire alarm systems on the market can only connect to application via Bluetooth. Since it only supports a short range between connected device, user will not be able to retrieve the notification immediately if they are away from their house. It is also not user-friendly if user must always switch on Bluetooth to ensure that they get notified on time if the presence of fire is detected. To solve the problem stated, the first objective of this project is to develop a system that detects fire occurrence using CCTV camera. Traditionally, fire alarm system has been developed using a combination of multiple devices such as infrared sensor, temperature sensor, and so on. Although using multiple devices can improve the overall accuracy of the system, but it's very expensive. Therefore, a vision-based fire alarm system is proposed to save money and lower the cost of smart fire alarm system. The second objective is to develop a smart fire alarm using cloud technology and connect to mobile apps to notify the homeowner in case of the existence of fire at home. If such a smart cloud solution exists, then the homeowner will be able to monitor their home remotely and locally when the homeowner is away or sleeping. The third objective is to develop a dashboard in the smart fire alarm system for monitoring the condition of the device as well as statistics of fire occurrence. If such a dashboard exists, the homeowner do not need to frequently check whether their fire detection device can work properly or not. Next, I would like to pass to the next presenter to continue our presentation. Thank you.
Hello, my name is Tan Xian, and today I would like to talk about our architecture diagram of our proposed system, which is the smart fire alarm system. So actually, as you can see, we have used quite a lot of services here, namely IoT Core S3 storage, recognition SNS, Glue, Athena, QuickSight, API Gateway, Cognito, and DynamoDB, and our obviously AWS Lambda. I would like to go through each services individually and explain how our architecture diagram function. So actually, AWS, I would like to first focus on the first row, which will be IoT Core, the store image to S3 storage, predict fire image. So AWS IoT Core is used to mainly connect device to AWS cloud. And how we do it is that first we set up multiple smart city camera. So this city camera, they will periodically, they will send upload video streams, and then they will convert it into frame by frame data. Then because due to the fact that the file format is in PNG format, we need to decode it, we need to encode it with a base64 format so that we can transfer data via JSON. Our AWS Lambda, which is a store image to S3, will then be triggered by an IoT rule and will then decode the base64 encoding JSON back into a JPG image. We will then store this decoded image into our S3 storage. This S3 storage will then again trigger our predict fire image. So in this predict fire image, we are now introduced to two new services, which is recognition and SNS. Recognition is a service that train and test model and is also used to classify image. So then what happens is that after we have trained and test our fire detection model, we then pass this image into a recognition model and try to see whether it's a fire. If it's a fire image, it will then trigger an SNS response and send out alert to our mobile apps alert devices, emails, and also our fire alarm system. So then when a new user, they want to sign up into our account, they will need to use Cognito service. So AWS Cognito is a service to authenticate user account, whereas API Gateway is used to deploy REST API on AWS Cloud. Why do we need API Gateway? Because we want to deliver a way for our mobile apps to be able to communicate with our DynamoDB. DynamoDB is a storage system that allows users to store data in a NoSQL database. Now, how do we visualize the data? Now, this is where we introduce to our last function, which is QuickSight. So the way we do is that we store our synthetic CSV in this S3 bucket, but it will periodically be generated from this DynamoDB. So then our Glue will run a synthetic crawler on our CSV data, which will then be connected to our Athena. Athena needs to be connected to data source, and we can use Glue to create data source. Then our QuickSight will then visualize our dashboard. And that will be all for our for my explanation on our architecture diagram.
Comparing the quantity service based on the research, Azure took the shorter times to analyze the photos but had the lowest accuracy, then followed by the Google, which was slightly slower but had the highest accuracy, then Amazon, which took the longest time but with the medium accuracy. So in terms of the performance, the Google Vision API show the most consistent and predictable performance, while Amazon Recognition and the Microsoft Azure show the reasonable performance. So for the IoT, AWS IoT is meant in connectivity, authentication, and development environment, and the use cases are the smart city, connected home, and the agriculture. So for the Google Cloud IoT is meant in connectivity and device management, and the use case are energy, smart parking and transportation, and the logistics. So for the Azure IoT Hub, it's meant in connectivity, authentication, device monitoring, device management, and the IoT Edge. And the use cases are healthcare, retail, and the manufacturing. The last one is the serverless computing. For the serverless computing, Amazon offer AWS Lambda, which having the maximum timeout of 15 minutes, while Google Function offer 9 minutes maximum timeout, and Azure having 5 minutes for consumption plan, 30 minutes for premium and dedicated plan. So in terms of the pricing, AWS and Azure pricing, additional request send at the USD of 20 cents per million request, and with a free quarter of 1 million per month. Then for the GCP, it offer an additional of 1 million free requests per month for 40 cents of the USD per additional 1 million requests. Thank you.
Okay, first I will show how we use the IoT to send the data to the fire image outlook bucket. So the bucket now is empty. Then first we will create the things, the smart cameras. Okay, and now we need to send the data to the fire image bucket. Okay, so the camera to gestures. So this code, it will send the image data, the red and the non-red. Okay, the red JPG to the bucket. So next we will need to install the camera certificate and connect the MPDD. So to debug this to connect the MPDD, this code here need to send with the here paste it. Okay, then the rules. You need to create rules, and this rule will trigger the Lambda functions, the IoT save image. Next is to subscribe to this. Okay, so this code will receive the message, and this is to send the image. Now we run this. Okay, so the data is sending. Here we can see, and it will be encoded to the base64. Okay, here. So we pass the data and the file name over here. Okay, over here the data from the MQTT is received, and this MQTT is trigger the rules and can be traced here. Okay, then click bucket. Okay, now we refresh. Okay, let's see the image is transmitted out to the bucket.
If we want to publish, then we create the publish. Now we can resist the message. So as I mentioned before, this code is to resist the message, and then this code is to send the image. Okay, so to debug the lambda function, we fix the CloudWatch. Okay, the code. Okay, due to the console over here, okay, so we can see, okay, click here, so we can see the successful message here. So when we click on the red.jpg, we download it, open. Oh, so this is the file image. Okay, thank you, that's all.
Now I would like to talk about how we use the connector to classify this red.jpg as a file image. So the first thing we do is that want to create a custom label dataset. We first create a new project, and actually because we already have our existing fire detection model, we just select this image. So we need to add labels. One of the fastest ways to do this is that we can import our label from my S3 buckets. First, we create two types of classes fire image, and we put the same amount of object property, which is 100, with our non-fire image. This is to prevent imbalanced dataset. After we have added the labels, we select this, and we can see that all of the image already automatically label fire and non-fire. So then the reason why it's 80 and 80 is because of the 80 20%. Then we just select the train model, but we have actually already trained our model, so I just select this fire detection model, then we press use model and we press start. So now our model is running. We can now copy this ARN and use for recognition API to execute the functions. So we just paste our ARN here. Then we press play. We'll be able to see that the image detected is non-fire. So then if, let's say, the image is classified as fire, what if our recognition detected a fire image? So what we can do is that we can set up a fire alarm to do this. We also first go to the AWS IoT core and we create our fire alarm thing. So that we download it and this alarm certificate here. So that we turn on our fire alarm, I type on fire alarm, and then we set up our fire alert at here in our email. So let's say if we detect a fire image, we can activate this fire response image, and we can see we will retrieve the fire alert and our fire alert will be triggered on. We also retrieve the email notification here. And just now the JavaScript function will show you it is what we use in our Lambda. It is what we do in this function here. So the upper part of the code will recognize and classify which is fire, and then we will send our fire alert email here. And the trigger of this will be the upload image bucket. So when an image is uploaded via the camera.js, it will then trigger all of the above state I just mentioned. That's all for my part. Thank you.
Hello, my name is Tan Xian, and now I'd like to talk about how our dashboard visualization work in practical. So as mentioned before, that our glue will get the will call the data from our CSV file, transfer it to Athena, and then Athena will transfer it back into our QuickSight. So actually, let's take a look at our synthetic data first. As you can see, we have multiple camera devices from 0, 1 to 10, and we have their location and latitude and longitude. So what does this timestamp mean? So actually, the way we do it is that we want to visualize when our camera will capture fire instances. So then when the fire instances is captured, it will mark the timestamp and the current address and the device information. So then we first store our camera fire dataset CSV into this synthetic bucket. Then we will run our synthetic crawler onto our synthetic bucket. When our synthetic crawler has finished running, it will generate this table, synthetic bucket. To make sure that our synthetic bucket is this, the crawl data is similar to our CSV data, we can check the column name captured. So as you can see, there is a total of 5 columns, and there are also 5 columns here. This indicates that our synthetic crawler is running as intended. Now I want to create a data source. So actually, after we have created our data, because what we need to do, we need AWS glue to create a data source, and Athena will then from that data source show the data. So if select run again, we are able to view all of the data in our synthetic bucket CSV data. Then when we want to create a new QuickSight, we just select Quick Analysis. We select New Dataset, select Athena. Let's go with Test, create data source. And it will show us all our available data source. Then we select Quick Synthetic Bucket and we select Edit Preview Data. We might need to, this step is for us to like edit the columns. Like see, this string is incorrect. We should select, change it back into a date. So now that everything is done, we just need to select Save and Publish. And now we are able to visualize our data. So for this data manipulation, I've already completed in our daily dashboard. Now I'd like to show you what each graph means. As you can see, because I mentioned that our camera unique devices is from 1 to 10, we have a total of 10 unique devices. And we split our fire objects by previous month and current month. From our previous one, you can see that we have 51 cases. Current one, we have 42 cases. This indicates that our fire system is working as intended. We have a decrease in the total number of cases. For this third graph is the total fire occurrence limit. This is the hard limit for how many fire outbreaks we can have in our system. If let's say we exceed this hard limit, that means that our fire system has some problems and we need to do some self-reflections. I have this graph that shows the fire occurrence by month. So actually specifically saying is the fire occurrence by day. For example, in this day, February 4th, we have 4 occurrence. This map shows where our camera devices they are located geospatially, and we can see that all of them are concentrated in Kuala Lumpur. This graph is about fire occurrence by location. As you can see in Bukit Bintang, we have a total of 7. This is an interesting insight because it may mean that, okay, there's something wrong with Bukit Bintang that caused such easy fire from happening. And lastly is this table. It's actually, because it's quite hard to know where our devices are located specifically, for the admin side, I give them this table so that they know exactly where their devices are located. And that will be all for my part on the QuickSight data.
Hello sir, my name is Lee Manjing and now I'm going to explain about the Cognito part. Cognito is used to generate user pool to store the data when users register themselves. And so we choose the manage user pool, and in the interface we choose to create a new user pool. But since we have already created an existing user pool, so we just proceed to explain about the inner part. After setting out the user pools, now we got the pool ID, and also we can connect it to the Android app. And as shown in the code, I will connect the Cognito with the Android Studio via the specific pool ID and also the client ID. So after installing all the libraries and dependency needed, the app can now functioning on our phone. So the launcher activity of the app will be the login page, and we can also create a new account. But since the daily email register limit has been over for today, so I will just demo the login part. So I enter an existing user, should be the username. So now the user registered in the user pool and with correct username and password will be logged in into the system, as shown in the screen here. And if new user is added, the details will be appear here. And upon successful registration for the new account, the user will be proceed to a verification page where a verification code will be sent to the registered email, and user will require to check their email and enter the code as listed in the email to complete the registration. Yeah, and once the verification is entered correctly, and the account status will be confirmed just like this. Now I'll continue to demonstrate how to use the API gateway to perform action on the user data in the DynamoDB. Firstly, we have connect a Lambda function called user CRUD API to the API gateway. So in the Lambda function, we have code for the GET request and also for the POST request. So now we can use the GET request from the user controller to retrieve the data from the DynamoDB table. Let's say if we didn't enter any value in the parent section, and when we press test, all the records in the DynamoDB table will be retrieved here. In query, you can also perform other action on the DynamoDB data. Let's say if I want to modify the user username, I can go to the user controller post request and then test. Enter the required details and change the username to hello, and then test. And here shows that the username has been updated successfully. And then we go to the DynamoDB table and press refresh, and here the username is updated to hello. Also, we can perform the delete action by changing the type. And then test and shows that successfully delete. And come here again, refresh, and the user 1 is no longer here. Also, we can add a new user through the post request. We just need to enter the details and then test, and details is displayed in the DynamoDB table. That's all from me. Thank you.